Okay guys, welcome to another parametric application example. And so we're doing another projectile. Basically, this time we have a dart that's being thrown. And we're just going to go through all the pieces of solving this one. And the template is very similar to what you did on page 32, where you saw the projectile equations. We'll use something very similar to those here and follow that template. So first thing I'm going to do is find our parametric equations, and it starts by just listing out the variables that we've been given. So I see my initial velocity, and so we use v0, and we're going to go ahead and list that as being 58 feet per second. All right, and then we have our angle, theta, which looks like it's going to be 41 degrees. And we know our initial time is going to be 0. G, remember this is a constant, this is going to be 32 feet per second squared. Okay, now that unit doesn't really mean much to us here, but it is important because it does cancel everything out when we set up our problems. And then our initial height, we're just going to go ahead and call that one 0 because they didn't really give us any other information. We don't know how high someone is standing, so we're just going to pretend like we throw it from a height of 0 and treat that level as being 0. And a quick reminder, so these are kind of our projectile equations. X is going to be equal to v initial cosine theta times time, okay, and our y is going to be equal to -1/2 g t squared plus initial velocity sine theta plus the initial height, okay, and there's a time here as well. All right, so these are our initial equations, and what we're going to do is we're just going to plug in the information that we know into both of these. So horizontally, my x is going to be 58 cosine 41 degrees times t, and we can plug this in our calculator and actually get a decent decimal approximation. So again, if I just put in 58 cosine 41 in my calculator, I should get x equals 43.773 times t as my variable. Okay, so that's kind of the most functional version of our x equation. And let's do the same thing with our y equation. So y equals -1/2 32 t squared plus 58 sine 41 degrees times t plus 0 for that initial height. And we can really do a lot to clean this one up. The first term very easily will become -16t squared. And then 58 sine 41 is just going to be equal to 38.051. Okay, and this last term, the 0 doesn't really count, doesn't do anything for us here. Okay, so this has a t with it, let's not forget that. And here we go, here is my y equation and my x equation in their functional forms, guys. The red equations are totally fine. They're just not necessarily simplified down, so we'd have to take the step of simplifying them every time we try to do any math with them. So as we continue with this, guys, part B says, can you draw a graph of this model? Okay, so roughly this is what our graph will look like, and you may use some graphing utility to help you, but if I was drawing this graph, my projectile starts at 0, 0, okay, and I realize it's going to leap forward and at some point hit the ground and continue the graph continues going, but actually we know that the portion once we reach over here is not going to actually be a legal portion of my graph, okay? That part technically does not count because your projectile just went through the ground in that case, okay? So roughly, my graph would look something like this. It's actually like a parabola, okay? And it's got that vertex up to the top, some maximum height. It's also got this point where we hit the ground, okay? And what we're going to do in the next section, we will solve for some more of this information. Okay, so C actually asks us, hey, what portion of this graph represents the problem's situation? Okay, so in part C, the first constraint I'm going to start with is that t is greater than 0. Okay, and so the reason I'm going to go ahead and put this and say, yeah, t needs to start from 0, and I'm including 0 in there, but we can't really go back in time, right? Like, you can't go to before you threw the dart and then you start going underground. And on the other end, we actually have a final value for t as well, where we have hit the ground, and we're going to put that in that spot right there. Now, we haven't calculated this yet, but we can definitely figure this out. So let's see how we can do that. So when the dart hits the ground, the height is going to be 0. So I'm going to use my y equation, and I'm going to put it equal to 0. And I'm going to have negative 16t squared plus 38.051t. And we can just solve this by either factoring or using the quadratic formula. In this case, I'm just going to factor. Because there was no height, it becomes pretty easy for us to factor. Negative 16t plus 30.051. Okay, so all I can do is GCF out of t. And so what I'm going to end up getting when I solve each individual factor, I'm going to get t equals 0. That's my first piece. And then on the other side, I'm going to end up with something that is approximately 38.051 over 16. And that is roughly 2.378. Okay, so what am I saying? The 2 points where my dart is on the ground is actually 0 and 2.378 seconds. Okay, both of these are seconds. And so what we've determined is one endpoint we already said was 0, right? When the time starts, when you throw the dart. And the second endpoint is where I hit the ground. After that, I'm not really flying through the air anymore. So 2.378. And that's the portion of my graph that makes sense. The portion where t goes from 0 to 2.378 seconds. Now, the other good part about this is, as we've actually solved part C, we accidentally got part D as well, where we asked, hey, when does the dart hit the ground? Well, it starts on the ground at 0 seconds, but it hits the ground at t equals 2.378 seconds, okay? That's the second time when you hit the ground. You threw it from the ground and then it lands at that time, okay? And then we want to ask ourselves, for part E, what is my maximum height for the dart? So here's kind of what we're going to do. We're going to say, hey, my two ending points I know are 0 on this corner and 2.378. Well, in the middle is my maximum point right here. And that one, it has to be halfway between those. Now note, these are t values, not x values, okay? So those are definitely based on the parameter t, not the x. Let's just note that, okay? We could figure out what x matches with that though. So this maximum point is gonna happen when t equals half of 2.378, okay? So if we do 2.378 over 2, we're going to end up getting 1.189 as my t value, okay? And we can kind of figure out everything from there, right? So if I wanted to figure out E, my maximum height, I can just take that time that we just found and plug it in for the time in the y value, okay? So what we'll do is we'll just do the y equals negative 16 1.189 squared plus 38.051 times that number that we just said, 1.189. Okay, and if we plug this in our calculator, we will get the maximum height should be 22.623 feet. Okay, so that is my maximum height. Okay, so my height right here is 22.623 feet. And finally, the last question that we've got here is going to be F, which says, hey, can you find the distance that you travel? Okay, well, the distance that we're traveling is just going to be the point where we hit the ground. So this time, horizontal distance, so we're going to solve for x, right? So this is F. X equals, and we'll use that equation that we got, 43.773, and we're going to plug in that final t value that we had, 2.378, when we hit the ground. Okay, so we just plug this in our calculator, and we get that your distance equals 104.092 feet. Okay, horizontally, that's how far you travel. And so basically, your projectile flies up to 22.6 feet in the air. And when it hits the ground, it's been flying for 2.378 seconds, and it's gone all the way to 104 feet-ish down the field. Okay, so this is solving stuff using a parametric. The key factor is once you determine the time when something happens, you can use that to determine the height, or you can use that to determine the horizontal position that you're at. Okay, if I wanted to know the maximum height or the distance at the maximum height, we could even calculate that by plugging in the 1.189 into our x equation. All right, so there is a lot that we can do with these. It's just about making sure you set everything up correctly. Okay, remember some key facts. Okay, when you hit the ground, your height is always 0. So if you're ever solving for the time when you hit the ground, you're going to do just like we did in part C. You're going to put those equal to 0 and solve it. And the two numbers you get, one is when you're launching right before you throw the projectile, and the second one is when you actually hit the ground. So make sure you take that second answer, the positive answer. Don't ever take the 0 as the time that you hit the ground. All right. Well, hopefully this example was helpful to you guys, and good luck and happy studying.